PreCalc. We are going to add to our knowledge of sine, cosine, and tangent curves by looking at a horizontal and a horizontal shrink and a horizontal stretch. So we'll see what that does to our equation and to our graph in just a moment. Before I dive into our main topic, I want to review just what we have discussed about sine, cosine, and tangent. It turns out that the sine curve looks like this, and the cosine curve looks like this, and the tangent curve looks like this. Alright, before I leave those, we've been practicing them and we come into class, and I need you to commit those curves completely to memory. And when I ask you about sine curve, in addition, I want you to be able to give me the amplitude and let me time this a little better. The amplitude and the period for each. There were other things I also am interested in, but for now, let's just review these two things, amplitude and period for each. So up here for the sine curve, the amplitude, you'll recall, was how far did it go from the center line to its highest point, or you can look at the distance from the center line to its lowest point as well. The amplitude, therefore, is 1, and it's found right there. How high is the mountain peak? Now we're not going from the lowest value, a total lowest value, to the highest value. We're going from the middle value to the highest. So that's the amplitude. It is a 1. Now, period was how many radians before the cycle repeats itself. So that will be its period. And we can see we start here on the way up, and it starts repeating at this point. How many radians is that? 2 pi. All right. Go ahead and fill in amplitude and period for the cosine curve as well. And I'll jump in here and tell you what it is. All right, the amplitude is from the middle to the highest point is again 1. And the period is how long before it starts repeating itself. It started at the mountaintop, went down to the valley, back to the mountaintop where it begins to repeat. This also took place in 2 pi radians. Alright, so when we go to tangent curve, we always find that he doesn't like to fit neatly into any of the little boxes we try to stuff him into. But that's alright, we need all kinds in this world. So tangent comes out to play, and his amplitude, how long is it from the middle of the graph, the middle line, till the highest point? Well, it goes on forever. So its amplitude, we'll say, is not applicable to this one. And the period is how long before it starts to repeat itself. Well, tangent, one full cycle of the tangent is easy to see with your eye. It's one of the snakes, like that. It's bounded completely on both sides by a fence, so those snakes can't get out and bite us. And those fences are called asymptotes. But can you tell me how many radians is it from, say, this asymptote to this asymptote? So this is 0, negative pi over 2 to positive pi over 2. So how many how many radians between asymptotes? Negative pi over 2 to positive pi over 2. Or perhaps you can see it clearly over in these two. And between these two asymptotes, how far is it from pi over 2 to 3 pi over 2? And when you look at it that way, can you not subtract 1 pi from 3 pi over 2 and get 1 pi over 2? So this is like 3 halves minus 1 half is 2 halves pi, which is pi. The period is pi. So the distance between these two or these two is pi radians. Notice its period is different than sine or cosine. No surprise there. All right, moving back, keep that in mind. The normal period for sine and cosine are 2 pi, but the period for tangent is pi. Moving back over here, our discussion so far has looked something like this, where if we had a number there, it affected amplitude. If we had a number here, it affected how far up or down we move the curve. And if we had a number here, it told us how far to the right or left that we move the curve. So the last player to come out and play this game with us is K. And K is going to be situated right here. And K's effect on the whole graph is stated above. It creates a horizontal stretch of the curve or a horizontal shrink of the curve. And so let's do an example and see how it works. K is a little off from A, B, and C. A, B, and C, we're pretty much, you look at the graph and you grab A and you use it. That's the new amplitude. You grab B and you use it. It tells you how far up or down to move the graph. C had a little twist for it because you had to remember whatever number was here, you use the opposite. So like if there was a theta plus pi over 2, we would use negative pi over 2 as our phase shift, and we would go to the left. So K is also, it gives us information about our shrinkage and our stretching, but it doesn't tell us directly what it is. So we have to have a key. So the key looks like this. This is the key to K. And there's a little formula, and there's a relationship between K and the period. Because as I take my sine curve that might normally go like this and stretch it, it gets a new period. If I shrink it, it gets a new period. So we need to know what the new period is. So what's the relationship, the key is, between K and the period? And it is always going to be K equals the normal period divided by, K is divided by, let's see how I do this. We'll say it's 2 pi divided by the period, where 2 pi is the normal period. That means we're talking about sine or cosine. However, if we're talking about tangent, I'll put it over here, K equals pi divided by the period. So this right here is the normal period. We're going to be working in sine and cosine this evening and tomorrow. So 2 pi is always going to be the value here. So you know we're working with sine and cosine where the normal period is 2 pi. If we pull out a tangent, this relationship changes. K is the normal period for tangent, pi, over the period. All right, so the new period is going to be caused, the shrinkage or the stretching horizontal direction will cause a new period. Once we know that new period, P, we can sketch it. All right, that's theory. Let's do one for real. Y equals sine of 1/2 theta. Notice K is in front of theta, and that is our K right there. So grab K. We know K is 2 pi divided by the period. K is 1/2. How do I know? There it is. I found the position for K, and there was a 1/2 sitting in it. I put it into my key, and this is a sine curve, the normal period divided by the new period. We have to solve this for P. You can multiply both sides by P and by 2, and that causes the denominators to eliminate, and we have P equals 4 pi. Some students like to cross multiply. 4 pi equals P. So that's another way you can get to this step, but you have to be careful with cross multiplication. Some students like to pull it out and use it when it's not appropriate. It's appropriate when you have a fraction on one side, an equal sign, and a fraction on the other side. Alright, so our new period is 4 pi. So I have to draw this function, the sine curve, with a new period. So, here's my sine curve. And I'm going to put in very lightly, or with a dotted line, our normal sine curve. So, starting there, it goes up to 1, down to -1, and the whole thing takes place in 2 pi radians. I'll kind of make them small. It's pi over 2, pi, 3 pi over 2, 2 pi. And so this function is sine. It starts at the origin. It peaks at 1, down through pi, bottoms out at -1, and back to 2 pi. And that is the one which I will dot, because it's not the real answer. So I'll dot it. Alright, not sure if that looks like a dotted curve from where you are, but that's my intention. So now we're going to see what the 1/2 does to this graph. It causes the period to go from normal 2 pi to 4 pi. So I'm going to put in some more tick marks. So this is 2 pi, this is 1 pi, 1/2 pi, pi, 3 pi over 2, 2 pi, so that's 4 pi, 5 pi over 2, 6 pi over 2, 7 pi over 2, and 8 pi over 2, which is 4 pi. So reducing 5 pi over 2, 6 over 2 is 3 pi, 8 over 2 is 4 pi. So if this was 2 pi, 4 tick marks later is 4 pi. So I've got to stretch this whole curve out, one mountain and one valley. Instead of within 1 pi, it's within 2 pi. Within 2 pi, it's within 4 pi. So I'm going to start at the origin, and I'm going to peak this time at, instead of peaking at pi over 2, it's going to take a lot longer to peak and to bottom out. So you see, I took that yellow dotted curve and I stretched it from 2 pi to 4 pi. That's what that 1/2 did. Alright, let's try one more example. I'll do a cosine curve and see if you can follow it through with 2 examples to bring to class tomorrow. Alright. Alright, running a little long, so I will shut down this part and pull out part 2.